Hello everyone, this is Pratima and welcome back to Planet Physiology. In today's video, we shall be exploring the fascinating world of hemocytometer. The term hemocytometer comes from three roots: hem for blood, cyte for cell and meter for measurement. So, this apparatus is traditionally used to count blood cells, but it is also versatile enough to count sperms and culture cells in research settings. While advanced laboratories now commonly employ automated cell counters like Coulter, which give more reliable and reproducible results, manual cell counting with hemocytometer remains invaluable. It is especially essential in the settings with limited resources or when quick, cost-effective methods are required. Moreover, manual counting provides a direct, hands-on approach which is critical in certain research settings and also while verifying the automated results. Let's study now the parts of hemocytometer. Hemocytometer consists of a counting chamber commonly known as Newburst chamber and two specialized pipettes, the WBC pipette and the RBC pipette. In this part, we shall study Newburst chamber in detail. As you can see, it looks like a thick glass slide, but it's not actually called slide, it's called chamber. So take a moment and think about why that might be. Once you are done, resume. That's right. Unlike a regular slide, which is flat and plain, Newburst chamber has depth. When a cover slip is placed on it, it forms a three-dimensional structure, making it more than just a simple slide, and hence it's called as chamber. Okay, now let's study it in detail. The first feature you shall notice is H-shaped groove that separates the central part of the chamber from the rest of the slide. These grooves are gutters and drain any excess of the fluid from the chamber. Separated by horizontal groove, you shall find two shiny rectangular surfaces in the center of the chamber. These are the cell counting surfaces. If you look closely against the light, you will notice a grid in the shape of plus sign. This is the actual cell counting area. As you can see in this side view, this is the central counting surface and these are the gutters. By the side of gutters are the slightly elevated ridges. You can appreciate the difference in the height of the ridges and the counting surface in the side view. When a cover slip is placed on these ridges, it creates a narrow gap of 1 by 10 mm between the cover slip and the counting surface. So it's a very narrow gap and because of this gap, it is called as chamber. Now let's study the counting grid in detail. Counting grid forms a large square of 3 mm by 3 mm dimension. Thus, the area of this square is 9 mm square. This large square is divided into 9 equal squares. So, each square has length and the breadth of 1 mm, resulting in area of 1 square millimeter for each. Out of these 9 squares, 4 corner squares are designated for WBC counting and are thus known as WBC squares. When viewed under 10x or the low power objective, you can see one entire WBC square. Counting the cells across this complete 1 mm square area can lead to eye strain and counting errors. To address this issue, each WBC square is further subdivided into 16 smaller squares. At this point, pause the video and try to calculate area and the volume of one smaller WBC square. It's a basic math. Great. I am sure many of you have got it right. Since each 1 mm side is divided into 4 equal parts, length and the width of each square becomes 1 by 4 mm. So the area is 1 by 4 into 1 by 4, which equals to 1 by 16 square millimeter. To calculate volume, we have to multiply area by the height of the chamber. Pay attention at this point now because this is very common mistake done by many students. When calculating volume, many students mistakenly use same measurement for the height as they did for length and width, that is 1 by 4 mm. However, remember that height of the chamber is determined by the gap between the cover slip and the counting surface, which is always 1 by 10 mm. Therefore, volume of one small WBC square is 1 by 16 mm square into 1 by 10 mm, resulting in 1 by 160 cubic millimeter. Alright, now let's move on to the RBC square. The central 1 mm by 1 mm square of the chamber is designated for RBC counting and is known as RBC square. This area is further subdivided to make the counting easier. However, note that these divisions differ from those of WBC squares, so pay attention. The RBC square is divided into 25 medium squares. These are outlined by triple lines for easy identification. Each medium square has dimension of 1 by 5 mm by 1 by 5 mm. Hence the area is 1 by 25 mm square and the volume is 1 by 250 cubic millimeter. Hope you understood this calculation because it is very similar calculation that we have performed for WBC square. Now since the RBCs are smaller in size than WBCs, they are always counted under high power, that is 40x or 45x objective. However, counting all the RBCs within this medium square could lead to errors and eye strain. And to make the counting more manageable, each medium square is further divided into 16 smaller squares. So at this point, take a pause and think about the dimensions of the smallest RBC square. Okay, very good. Since each of the medium size square has a side of 1 by 5 mm and it is divided into 4 equal parts, length of each smallest square becomes 1 by 5 into 1 by 4, that is 1 by 20 mm. Thus, the smallest square has dimension of 1 by 20 into 1 by 20. The area becomes 1 by 400 square millimeter and the volume becomes 1 by 400 into 1 by 10, that is 1 by 4000 cubic millimeter. Now you may wonder that why do I need to know these areas and volumes? I believe I am here to learn medicine and not for any mathematical calculation, isn't it? If you are getting this question, then just recall the normal values of various blood cells, say for RBC or WBC. Yes, RBC count is about 5 to 6 millions per cubic millimeter, while WBC count is about 4000 to 11,000 per cubic millimeter. So notice the unit here, it is per cubic millimeter. To accurately measure the counts in this unit, Neubauer's chamber is calibrated in millimeters. So knowing these dimensions is essential for accurate calculations of the cell count. So okay, now you know the importance. Let's see how exactly this chamber appears under the microscope. So first I am focusing the chamber under 4x, that is very low power objective. And as you can note, you can see the entire chamber. You can see these are the corners which are cut off. These are actually the WBC squares and in the center is the RBC square. But routinely you focus the chamber under 10x. So let us see how it appears in 10x. So here is the chamber under 10x objective. And as you can note, you can visualize 1 mm by 1 mm area at a time. So this one is WBC square, this is another corner square, the third corner and the fourth corner square. I am moving now into the center for RBC square and here you can see the entire RBC square, 1 mm by 1 mm area. As I mentioned earlier, RBCs are counted under high power objective. So let's see this RBC square under high power. So I have focused the RBC square first under low power and now I am just switching it to the high power. So I am bringing 40x objective in position. And as you can note, you can already see some lines, just you need to adjust the light and the fine adjustment to be done for clarity. And this is your RBC square under 40x. Now you don't know which part of the RBC square you are actually visualizing. So start moving towards any one end. As I am moving the chamber, reach to the end. And now corner square. You can make out that above you can see only vertical lines and on the side you can see only horizontal line. So you are in the corner square. Once you locate any one corner square, in the same way you move on to the other side to get the other corner square. So this is all about the new bus chamber. I hope you find this video useful. Thank you for watching and join me in the next video where I shall be discussing pipettes in the hemocytometer. Are you new to my channel? Then please subscribe it and press the bell icon to stay updated about the new releases. If you like the video, give it a thumbs up and share it with your friends. Thank you for joining in and see you in the next video.